Hello class, this is Miss Aya with today's video on 9.5, Power Series and Intervals of Convergence. As you're watching the video, please take down notes, writing important information, vocabulary, formulas, equations, and examples. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what occurred. And at the conclusion of watching the video, write a brief summary of what occurred in the video in your notes and submit that summary as well as a top question via the online WISC form. That being said, let's begin. So this section is on intervals of convergence, which is a new term, but it's not too difficult a term. We've actually already been dealing with intervals of convergence. But before we start the topic, let's refresh or bring to memory the ratio test, because you're going to need to know it when we use intervals of convergence. So just FYI, the ratio test, if you remember, for a series, if we can take the sequence of ratios, of consecutive ratios, and if it equals a number L, if that number L is less than 1, then the series converges. And if L is greater than 1, or if L is infinite, then the series diverges. And if L is equal to 1, then we can't determine anything regarding this situation. A thing also to note is that in the ratio test, you can't have a term being 0, as you see here, because then we can't calculate the limit and we don't know what information about the limit. Okay, so let's talk about first a power series. If you recall, we've been working with a geometric series, which looks like this, where the term A is the initial term and X is the common ratio. And we found that, and we've been using the fact that this series converges only when that X value is between -1 and 1. But what if you have a series that is not a geometric series? How can you determine whether it will converge, and if so, for which X values? So let's take a look at another genre of series, and it's called a power series about a value X equals some A, where A is a constant number. And again, because it's a series, it's the sum of a term, and the term is a constant times a power of X minus A. So it looks something like this, where each term involves a constant being multiplied by X minus A, a power of X minus A. So this is what the series looks like in general, and here is the term that we're talking about in this case, where C sub n represents a bunch of constants. Okay, so that's a power series, and the question is, does a power series converge? And if so, where does it converge? So let's just take, again, consider this the partial sum of a power series. Let it be some term S sub n. So if we're going to take a look at S sub n, which can be computed for any n greater than 0 up to here. And this is a thing that I want to point out too. If you notice, we're starting with a n equals 0 instead of n equals 1. And the reason being is that it just makes stuff a little bit easier. If we're talking about the nth term, we want to end with a power of n and a power in the nth constant. So anyway, so we have some initial term, which is C naught or C0. So if we consider the sequence of partial sums, so S naught, S1, S2, S all the way up to Sn, all the way up to infinity, we'll see that it's based off a value X, which is our independent variable, and as you can see here. So the question is whether or not this series converges, this sequence converges, depends on X as well. So let X be some fixed value. And if this sequence of partial sums converges to some limit S, then we say that the power series converges to S for this value of X. Okay? So let's consider an example. So let's consider this series. Now, if I want to come up with an expression, I can see here that I know it's power series because it's a power of X minus some A. So it's a power series about X equals A, X equals 1. And then as you can look at it, the C can be expressed, if you see here, it's 1, and then it's -1 over 2, and then +1 over 3, and -1 over 4. So the way that you can determine the constant C sub n is this expression, -1 to the n minus 1 over n, and then this is the power part of the power series, okay? So the question is, will it converge? When will it converge? Well, if I were to just and graph the function s sub 14, actually, let me start with s sub 5. So 1, 0, 1, 2, 3, sorry, 1, 2, 3, 4, and the fifth term up to here and cut it off. This is what the graph would look like. Okay, sorry. All right, and if I were to do the same thing, but this time up to the 14th term, then this is what the graph would look like. Okay, and vice versa. And if I keep going on for the 8th term, and also, let's take a look at what's this other, oh, the 11th term, it looks like that. So it looks like this term seems to have some type of limit value once we get around, but once we get past this point, it seems to go to infinity. And so that will let us know that it seems to, the series will converge for values less than 2. And for values greater than, let's say, 2, whatever this point is right here, it diverges. As you can see, it goes to infinity. The sum, the partial sum, as S gets, yes. So let's take a look at a table of values, and let's try 2 different x values. An x value that looks like it would converge, so any x value around 2 or less than 2, and an x value greater than 2. So we let x be equal to 1.9 and another x be equal to 2.3. And so if we take a look, here's our 1.9 column, and here's our partial sum of 2.3. And as we look at it, as n gets bigger and bigger, if we just focus on this term, as you can see, as n gets bigger and bigger, our partial sums seem to kind of converge around, or don't get bigger than 0.7, okay? But when x is 2.3, you can see that as n gets bigger, the partial sums seem to oscillate and don't seem to kind of gather around a value. So that gives us an idea that something's happening for an x value less than 1.9, and something's happening for x value greater than or equal to 2.3. Okay, so here's some terminology. We said that the interval of convergence in this case is for all x values between 0 and including 2. And if we look up here, we can see that between 0 and 2, it seems like all the different partial sums seem to converge around the same value until they get to anything past 2, and then they seem to go do their own different things as well. So that's where we get that from the graph. And we said that the radius of convergence of this series is 1, because the length of this interval of convergence is 2, so halfway between of the interval is 1. Okay, so terminology that you're going to need to know, we're going to go over it. So I guess the best question that you're probably asking is, how do we determine the interval convergence without having to list or try all these different partial sums? Okay, so before we can determine that, let's go over some terminology again. We say that the series converges only for x equal a if the radius of convergence is defined to be r equals 0. So in other words, if the series only converges for one x value, and that's at a, then we say that the radius of convergence is 0, r equals 0, which makes sense because there's only one value that it converges for. If the series converges for all values of r, then we say the radius of convergence is defined to be infinity, which makes sense because there is no halfway between the lower endpoint and upper endpoint because it's all values. And then there is a positive number called the radius of convergence such that the series converges for all x minus a less than r. And this is for the absolute value, so we can put a negative r to less than x minus a less than r, and diverges for all x values such that x minus a is, the absolute value is bigger than r. So a good example would be this graphic right here, which kind of represents that for a r value, which is a which is not 0 or infinity. Okay, so this is, in this case, this drawing only works for this situation. Now, the interval convergence is an interval, and it's between the values a minus positive r and a plus positive r. So that's where we get the radius of convergence from. All right, so let's take a look at an example right here. And as you can see here, this is a very familiar series. If I want to express it, I can. The radius convergence here is x values between -1 and 1, so the absolute value of x less than 1. The radius convergence in this case is 1. Let's take a look at another example. In this case, when will this series converge? And using the fact that this is a geometric series and this is a geometric series, and we know that this geometric series converges when this value is between, or this common ratio is between -1 and 1, then it makes sense that this this series will converge when its common ratio is between -1 and 1. And the only way that that will occur is if this x over 3 value is between -1 and 1, or absolute value of x over 3 is less than 1. Well, if that's the case, then that means that the radius of convergence is 3. And I just wrote up the math that we did to get why it's 3 up there. In that case, and we use the fact that this is geometric series with a common ratio of x over 3. And we need to determine when that common ratio is between -1 and 1. Okay? So if you recall, the power series terms looks like this. Okay? So how can we determine if a power series, what the radius of convergence is? And the way that we do this is by using the ratio test that I referred to earlier in the video. So since a sub n represents a term of the power series, I'm going to use the ratio test with this term. And because it's x minus a to the n plus 1 over x minus a to the n, then that simplifies to just x minus a times the ratio of the coefficients, the n plus 1 and its next coefficient, previous coefficient. And so we already know that x minus a is going to be some type of constant value as n goes to infinity. And then it's going to give us that the limit of this ratio quotient is going to be equal to the limit of the ratio quotient of the coefficients times the absolute value, again, absolute value of x minus a. Okay, so why is that important? Because now that gives us, lets us know that the radius of convergence is dependent on the convergence of the coefficients. So if I were to take a sequence just of the coefficients of the power series, then that will help me determine the radius of convergence and the interval of convergence for the power series, which is kind of cool. So we have 3 cases. Suppose this ratio is infinite. Well, it either means that this is infinite, which doesn't make sense because these are 2 constants, or this is infinite. If this is infinite, then the ratio test shows us that the power series only converges when x is equal to a, because then this term will be equal to 0 because of this. Okay, so the radius convergence is r equals 0 if this is infinite. If the radius, the ratio test goes to 0, it means that the ratio that the power series converges, and that's just one of the rules of the ratio test. And we say that the radius convergence is r equals infinity because it doesn't matter what x is, you will always have that situation. And last but not least is case 3. Suppose the conversion to some value k. So then the coefficient ratio conversion to some value k, that basically means that you're going to have some expression that looks like this. So that will let us know that k is where the coefficients converge to, the ratio of coefficients converge to. And that k is represented by you can use k to define r, okay? And we have something that looks like this, okay? So that means that it will only converge for that k value. All right, so in conclusion, And this summarizes that. We'll look at the rest in class tomorrow.